Okay, so for this tutorial, we're going to look at the family of apply-like functions, apply and its family of functions in R. Now, as we've talked about before, R is both an object-oriented language, but it has these aspects of it which are similar to other functional programming languages. And this is one example of it in which we've sort of got functions that allow you to do certain things across, say, elements of your data or of your objects, or cross sets of objects in very easy ways. And this comes out of these families. More important to us, though, really than how they built it, is really what are the uses of these functions, these apply-like functions. And really comes down to is when you're going to do something repeatedly, the same or very similar sorts of actions, say calling particular functions, making certain kinds of plots, across large data sets or large kinds of grouping, you want to often do exactly the same set of things. Say, if you have a large data set, you may want to do it for column 1, column 2, column 3, and so on. Well, there are functions that allow you to do this in various ways, and this is the apply family of functions. And here's an example of many, although I don't know if it's all of them, that are available. We're only going to look at a small set of these. For this example, we're going to use this data set, the dll.data data set, which you should already have access to either on the course website. So we'll just call that, and we're not going to really worry about these details about what we're doing. We're just going to grab the data set. But let's take a quick look at the data. All right. So we use the structure function to take a look at it. Again, we know there's 1918 observations, so that means 1918 rows, 11 variables. That means there's 11 11 columns in this. It's treated as a data frame. We may want to do certain sorts of things. So for instance, we may want to ask about some summaries for each of the 11 variables. Obviously, we can just use the summary function for this. But as an example here, let's use the apply function. And the apply function is quite simple to use. So literally, apply, the first argument that goes into this apply function is, is the object that you want to be applying the set of functions to. So this, in this case, is our data frame. It can be true for matrices as well. And I think you can use it for lists. I'm not sure about that, though. There are specific ones for lists, though, that we'll learn about later. Then you specify how you want to do it. So with the basic apply function, you specify a margin. Margin 1 would be row to row, so if we wanted to do something for each of the 1918 rows, we could do that, and that would be margin equals 1. Here we want to know about the 11 different variables which are for each column, so we're saying margin equals 2. So we'll go column by column. And again, in in the Mac window, you'll actually see right below the important argument. So the big X down there is the object you're applying it to. Margin is just like this. And then what the function is. And the function that we're going to use here is summary. We're just going to ask for the summary. And if we do that, what we get out of this, it would be the equivalent if we asked for each column from the object, from the dll.data object, and just called summary on that. And so the first one, we get the name, the length, class, mode, etc., etc. So it gives us slightly different information than we would, if we did the same thing for the overall summary. And you'll see that if we go summary of dll.data. And I hope that by this point people realize why it would give these different things, because dll.data as a whole is one type of object, and its class is data frame. And so there's a specific method for data frames. So the summary it's really calling summary.dataframe or something similar to that, and does it in a certain way. What we've done by this apply function instead is, because we've asked for column by column, it basically looks at the class and the mode of that particular variable of that column, and we'll call the specific method for that. So it can provide slightly different results, but that's neither here nor there. I was just more trying to show you of doing the column by column sort of implications. If we do it, let's clear this out. If we do this just for the numeric columns, so that here we're calling apply, but only through columns 5 through 8, again, look at the index there, we can do the summary, and this should give us numeric summaries. So it's giving us some information about these numeric summaries. And we can apply it for not just, say, summary, but really any function. So here we're just going to do the same thing for standard deviations, and we actually get the standard deviations for the log transform femurs, femur length, log form tibia, and the raw tibia length. It's really designed for matrices, arrays, and it actually coerces data frames, as we just did above, to be in a matrix. And so you have to be careful because, of course, that will do some funny things if you're doing it. Of course, we can use this for custom functions, so we'll use the two functions that we love to write here, which is one for the standard error of the mean and the other one for the coefficient of variation. I'm not going to go through any details there. Let's just clear out the window so we don't make a mess. And we can just use those exactly the same way. So now we've actually computed, for those same four variables, the standard error of the means, or the coefficient of variation. And this can be very useful for really any function that you think of. So for example, people doing association mapping or other genomic studies, depending on how the data is organized, this could be fruitfully used. I do want to make an important point here for very large, even fairly moderate data sets, that the apply family of functions actually dynamically grows the output vector or matrix. So whatever it's going to be storing things, and it's dynamically growing. So it's not sort of an element by element growth, but it is growing it dynamically, and that can be reasonably fast for small data sets, but it's really terrible for big data sets, so you want to be careful. In those cases, it's best to allocate memory for your output object and actually fill it. So you pre-allocate your output object of the right dimensions and then fill it. And that's a much faster and much more efficient way of doing it. Not super important for our particular class, but in general that's useful. So often we're not actually interested in applying things just based on particular rows or columns, but in many data sets we actually have particular treatment levels. So for instance, we have different genotypes that we might be looking at, different strains, different environments, whatever it might be. And so what we might want to do is have apply functions that make it easy to do that. Now the traditional way to do this without an apply function would really be to use a for loop, and we would do something like this. We would say, okay, we have different levels for one particular factor, in this case the variable line. And so if we go n levels, this basically says how many different levels of line are there. So big N, if you look at it, it's going to be, I think, 27. There's 27 separate levels to line, and line is a factor. And what we'll do is generate an empty vector of length n that we're going to store all of the means for each line, for each strain. Line is just a different name for a genetic strain. And we do that, we're just storing that. We'll actually also store, we'll have to do it, I'm not going to go into the detailed reason why at this moment, but we're actually going to store the names for each of those levels of lines. So if you look at now lines, SCT, means, you'll actually see, oops, sorry, I miswrote that, there we go. SCT means, you'll actually get each line name, and right now it's NA, because there's nothing in here. The line above, we just created an empty vector of length 27, because that's how many lines there were, or distinct lines there were, and each has an NA. And then what we do is now, once we've done all of that, then we actually compute the line means and store them in that object we've created. So we use a for loop, so we say for I in levels, each level of DLL.data $line. We will go through it. For line I, compute the mean. Given that line equals I, it's kind of an annoying way of writing it, but you can do it. And then you just run through it. And now if we actually look at lines SCT means, we get each line. So each line and its corresponding mean. It's not terrible, but there must be easier ways of doing it. And in fact, there's a really good convenient function called tapply, which really is, the goal of it is to apply whatever function along different factor levels. And see how much easier all of this is with just this one thing. So we go with DLL.data, so with our object that we want to use, we're going to use tapply. This is just saying we want to grab it, so we're going to grab SCT, so we want to compute something to that particular variable, the SCT variable. That's the sex cone teeth for this data set for fruit flies. Our index variable here is neither rows or columns, but in particular is the variable line. Again, that's just the name for strain, and the function we want to compute that we want to use is mean. So we do that, and we get exactly the same output we just saw before. For each line, we get the mean value of mean number of sex cone teeth for each line. And that's really convenient, so we can do that all in one line instead of having to write those multiple lines. The nice thing about this t-apply is we can do what we call crossing of factors. So say we wanted combinations of particular factors. We didn't want to know just what the means were for each temperature or each genotype, but for combinations of all possible temperature and genotype. So here, this experiment, flies were reared at 2 different temperatures, and there were 2 of these different main genotypes, a mutant and the wild type, and we want to compute it. So we expect 2 by 2, so 4 means, and we do it, and indeed we get 4 means out for each possible combinations for those fruit flies raised at 25 and 30 degrees each, and for each combination of mutant or WT, which stands for wild type. And there's different ways of doing this. You may not like that. In that case, it produces a single vector of length 4 of the combinations. You may want to produce it in some kind of table or as a list. And so what you can actually do is list the particular combinations of those variables. So instead of using the cross or using the colon to get the interaction of possible combinations, you basically say, use the list function to say, do it for temperature and genotype, and it will compute a nice little table of those combinations. And this can be very useful for larger things, and you'll see this in one moment. It's much more useful for things beyond these 2 by 2 tables. So in particular, I'm going to show you an actual interesting example. When we did this experiment, what we were interested in is really asking how this mutation, this DLL mutation, would potentially increase the amount of variation for sex cone teeth, not just how it changed the mean number of these sex cone teeth, but how it actually changed variation for it within and between lines. And so what that obviously, or what obvious to us at the time, at this point in the course may not be obvious to you, and that's absolutely fine. What we really wanted to know is, okay, looking at all possible combinations of the different strains we used via as related to the different genotypes, and by genotypes, again, we mean mutant or wild type, how did variation change? And here, instead of using the straight-up variance, we're using the coefficient of variance, so it's just scaled by the mean. And we just do that, and we'll just call that exactly like we did above, and we'll call this cv.set, and we do that, and let's take a look at the object that we get out of that cv.set, and we're going to get this nice table out, which is essentially a matrix with 2 columns, one for the DLL, one for the WT, and for each line. I think it actually should be as a matrix, and probably saving it as, I can't remember for sure, but should save it as numeric. Good, so it's doing it in a nice, convenient way. So why is that useful to us? Well, we can ask the question, if our hypothesis is that the mutation should not change the variance in the trait per line, then we'd expect to see some sort of overall positive correlation for each line, whether it's the DLL mutant or the WT wild type. So we can essentially do a plot of that, and then we'll actually put a line in here where it has an intercept of 0 and a slope of 1, and if we're right, things should fall more or less along the line with some sort of stochasticity. And we bring the plot over to this window to take a look. Well, and what do we see? Sorry, the fonts might be a little bit small for yours. On the y-axis is the wild type. On the x-axis is the DLL mutant. We expect things to fall along the lines, but hopefully you can see clearly here that those little circles are far off the line. In fact, basically almost in every case, the DLL mutation increases the amount of variation for this trait relative to the wild type, which is nice, and a nice graphical depiction of this point. Okay, it's actually pretty cool in my mind if you think about it. So you can think about different ways of applying that, and for time for this tutorial, I'll just skip this, but please pause this and try this and play with this. This can be extremely useful applications, and again, I won't go through this part, I'll let you run through this yourself, but a good example of where this can be used is for computing Levene statistics for more complex designs, and I'll let you read through that and take a look at the function itself. It's not super germane for the moment. I do want to get to the next one, so we're starting at about line 140 with the by function. So the by function is actually just a wrapper for the tapply function that we just used, but it can actually make things a little bit easier, in particular if you're running the same model, the same statistical model over and over and over again, but with different data sets or subsets of data, which is very common in microarray analyses, so the gene-by-gene models. And so what I'm doing here, I'm using the by function, again on the dll.data dataset. The indices that I want to do it for is line, so I want to compute some model for each line. And that function that I'm going to do, I've written out in a slightly different format that you might be used to, is I'm saying the function with the input of x, and that just it's going to just do this based on the different lines, is I want to look at the regression of 6-comb teeth back onto genotype. So modeling how much variation, or accounting for variation in 6-comb tooth number based simply on genotype for each line. And then I'm going to store all of that. So we run the model and it gets stored in this model.extract. Now this model.extract object is actually a big list where it actually has all of the output for each line as a list. And you can actually look at the dimensions of this. And it has 27 dimensions, but you should also make sure that you know what's going on when you're thinking about how you extract from it. Model.extract. Well, it's actually of class by. I didn't even know that. I thought it would be a list. That's probably a specific list-like object. But we can use this in pretty straightforward ways by using actually another excuse me, another apply-like function called sapply. And what we're going to say is, okay, maybe what we want to pull out is the coefficients, or the parameter estimates, for each of those 27 models. And so by looking here, you can see here's the coefficients, COEF, so we can use the coefficient here, and it's the second one we're interested in. We're not so interested in the intercept, but we are interested in the coefficient associated with the genotypic effect. For one particular model, the last one will be negative 2.405, but we want it for all 27. So we do this, and what we get is a vector now of those coefficients by line. Some are negative, some are positive. We haven't asked anything about uncertainty associated with it, which is not the point of this tutorial. We can also extract all sorts of other things. Anything that would be held in the standard, the LM model object. So any of the output from the linear model object is stored in this much larger object. So you can kind of consider this a big catch basin for everything, but everything's stored in such a way that it's organized that makes it easy to pull out. So we can just do that. Now we've extracted the log likelihoods, or we could do anything else. And we could do these for, again, much more complicated combinations. So we could do it by genotype and temperature, or anything else we really needed to. And like I mentioned before, this sort of approach, very, very useful for small to moderate sized data tables, maybe 1,000 factor levels or so, because it's faster to write, even if it's longer to run, so fast to write that you don't really have to worry. But for very, very large ones, it can be where you're talking about tens of thousands or millions. Probably it's best to go back to sort of a standard for loop. I'm going to skip this sapply example, but please take a gander of it. This is just showing how to use do a power analysis with a built-in function for power.t.test, which we'll come back to later in class, and it just shows you how to do sort of a power analysis across a range of values. We can come back to that later. lapply, here's just making the point that it'll do the same thing as sapply, but outputs it as a list. What I did want to show you finally in the last minute is how you might use the replicate function, which is somewhat different in what it's going to do, but it's the same basic idea of you want to replicate some function over and over and over again. So here the goal isn't so much to take an original object or data set and run on subsets of the, either by variables or columns or rows or by particular factor levels in it, but instead you want to do the same operation over and over and over again. So this comes up a lot where we're going to want to do simulations of a data set and do it over and over and over again. So the example here is we're going to want to generate, using our norm, 100 random normal deviates from a normal distribution with, in this case, a mean of 5, which is this argument here, and a standard deviation of 2. As you can hopefully see from down here, it might be too small on your screen. So it's just going to generate 100 numbers from a normal distribution with mean of 5 and standard deviation of 2, but we want to do that 4 times. So we do this, we run this line, replicate, and if you now look let's actually look at the dimensions, dim, of sim.normal. You'll see we now have an object which has 100 rows by 4 columns. So each column represents a set of 100 random normally distributed values from a distribution of mean 5 and standard deviation of 2, but separately done, which is much like the way we're going to think about sampling in our course. So sort of it provides a very convenient way of doing sampling and simulations. And if we actually look at sim.normal, column 1, say you're going to have 100 random variables, we can do 100 additional ones, which will be different, coming from the same basic distribution of mean of 5 and standard deviation of 2. All right, we've already gone to 20 minutes, a little longer than I wanted, so we'll end here. I would suggest playing with the one above here, in particular the sapply, as it's used for this power example, and play around with things to make sure you see what's going on, in particular how changing, say, your sequence here might change how many outputs you get. And we'll talk later.